Hello, we are Team 4 consisting of Manvit Reddy, Saransh Rajput and Shorja Mukherjee, and we are here to present the paper Rational Behavior in Committee-Based Blockchains for our reading assignment in the course Distributing Trust in Blockchains. About the paper is Rational Behavior in Committee-Based Blockchains. The paper was authored by 4 French computer scientists and it was published on June 13th, 2020. So, a little introduction / abstract about the paper. The paper studies about the rational behaviors of participants in committee-based blockchains. So, what are committee-based blockchains? We'll get to that soon. But committee-based blockchains essentially rely on specific simple blockchain consensus algorithms that are guaranteed in the presence of rational participants, and we'll be explaining all these terms like rational participants later on in the presentation. So this paper in specific considers simplified blockchain consensus algorithms based on existing or proposed committee-based blockchains, and which encapsulates the two main actions of the participants of the blockchain, which is 1, voting for every block, and 2, checking the validity of the block, whether the block should be placed or shouldn't be placed, and whether it is valid to be placed or not. So the paper's main focus is on the fact that there are costs attached to these actions, the actions being voting for a block and sending the message, and the second action being checking the validity of the block. And players behave in a way such as to minimize these costs, because obviously players, and that is what rational players are players that want to minimize costs and maximize rewards. So where do players get rewards? Rewards are received when a block is published. So the paper itself is talking about a pre-renowned concept, but the way it's novel is that it tries to find an equilibrium. In this case, we use something from game theory called the Nash Equilibrium among different reward schemes which are experimented in this paper, and it also introduces the notion of trembling participants. Now, trembling participants has never been looked at in a blockchain paper before, and this is the novelty of the paper. Trembling participants are participants who are rational, who, like I said, are participants who want to maximize the reward, but sometimes do unintended actions with a low probability. So they can propose a block that is not valid with a low probability even though they don't want to. So before we get into the crux of the paper, I want to introduce some key terms which are very essential to the understanding of this paper. So what is blockchain? Well, obviously this is something we all know. A blockchain is a growing sequence of blocks where each block contains transactions and is linked to the previous block by the hash. Modifying any information in any block will cause the whole blockchain to be recalculated, so that will take a lot of time, and that's why it's immutable. So what is the height of the blockchain? So in committee-based blockchains, the height of the blockchain is defined as the number of blocks that have been created before this, or like the slide explains, since the genesis to the current block. And now what is committee-based blockchain? So there are two main types of blockchains. One is forkable blockchain and one is committee-based or non-forkable blockchains. Forkable blockchains are your common blockchains like Ethereum, Bitcoin, etc. Whereas committee blockchains, for each height or for each new block, a committee is selected, where a committee can be a certain portion of the participants or the full number of participants. And this paper doesn't really talk about the selection of the committee because it's out of scope of this paper. But a committee is selected, and this committee is in charge of agreeing on which block to append next. So they have the purpose of avoiding forks because the committee only publishes one block at a time and decide what block to add next. So how do they decide it? They run blockchain consensus algorithms, which we'll talk about later. So in your forkable blockchains, you have two different concepts for consensus, and one is proof of work, where a participant needs to prove that they have worked to have the right to add the next block, and proof of stake, where the more you have invested in the blockchain, the more likely and it is for you to give you the chance to publish in the blockchain. Some other important terms which are very relevant to this paper in specific: rational users. So like I said, rational users are trying to minimize loss, which are the two factors I discussed before: sending a message and validating a block, and trying to maximize their profit. Profit is received when a block is mined. These participants don't want to harm the system. In fact, they're trying to grow with it, but like any rational user, they will try to extract the most they can. And this is in contrast to an honest user, where an honest user is not looking at his or her personal gain, but is rather following the exact protocol that has been set out. So, and now coming to trembling hand. So, what is a trembling hand? A trembling hand is actually taken from psychology, but is a concept taken from psychology, and in this paper, it is a participant who is a rational participant, but with a low probability the player can tremble or have a error or do an unintended action, and we will discuss more about this later. And what is Nash equilibrium? Nash equilibrium is a concept of game theory where the optimal outcome of the game is decided is one where no player has an incentive to deviate from its chosen strategy after considering an opponent's choice. So essentially, when Nash equilibrium is attained, when you know what the other player is doing, but you cannot make any move which will cause your profit to go up. So what are the basic contributions of this paper and what is its novelty? So the paper analyzes the behavior of rational participants in committee-based blockchains. It shows the different equilibria that exist given different methods of rewarding the committee members, which we'll get to. And it analyzes if the equilibria do satisfy the consensus specifications. Again, we'll get to that. And additionally, they introduce the notion of trembling hand, where with low probability a player can tremble and do an unintended action. We do the same equilibrium analysis for only rational players and players who have a trembling hand, who are rational players who can make mistakes. And in both cases, we find out that there always exists equilibria, but they might not always satisfy the consensus properties. So let us now prove that there is no more equilibrium. To do this, let us define a set called X of send, where this set consists of all the players that have decided to vote. Suppose this set has less than v minus 1 voters. Let's assume a player who wasn't voting, say I, decided to now vote. And let us assume that this causes a Nash equilibrium. Since X of send is less than v minus 1, the player who has decided to vote, whose gain would have been 0, is now minus of C of send, because he has not actually swayed the vote, and that's why there cannot exist Nash equilibrium, because if he decides not to vote, the gain would be 0. And in the second case, where it's greater than v minus 1, assume by contradiction that there exists a Nash equilibrium such that player I does not vote, say false. The gain at the equilibrium is now 0. If instead he deviates and votes, his gain will now be r minus C send, which is greater than 0, and therefore a player is gaining by unilaterally deviating, and therefore we are not at a Nash equilibrium. It's also important to note that in our first scheme here, in our second scheme where no player votes, we are not actually reaching any termination, whereas when all player votes, we are reaching a termination and our consensus. Now let's look at a reward all committee members scheme under the rational subsection with v equal to 1. So again, there exists only one Nash equilibrium, which is when exactly one player votes and others do nothing. This will be getting a little repetitive, so I will only talk about the novel parts. So here, let us assume a player with index 1 votes true, and right now his gain is r minus C send. If he decides to deviate, his gain would go from r minus C send to 0, and therefore he is not gaining anything. and if someone who is not voting decides to deviate, his gain would go from R, because he doesn't incur any sending cost, to R minus C send, and that's why we are at a Nash equilibrium. And to prove that there are no more Nash equilibriums, it's very similar concept. So let us now get into the crux of the paper and define a system architecture for our blockchain. We consider a system composed of n players who are all part of something called a committee, who are defined with the index I and take values from 1 to n. There are two main components of the system that this paper observes and plays with, one being communication and the other being player behavior. Communication. In communication, the players communicate by sending and receiving messages through a synchronous network. So what is a synchronous network? A synchronous network is a network where once a player sends a message, the recipient to this message receives the message before any other important event occurs. Essentially, this means that once a message has been sent, the recipient will receive the message without any overlap to any other phase where the value of this message is used. A round consists of three sequential phases: the send phase, the delivery phase, and the compute phase. We assume that all the messages sent will be received before the end of the delivery phase, and we are making this powerful assumption by saying that our network is synchronous. We assume that every broadcast is reliable, which entails that two of the following conditions hold. One being safety, where every message delivered by a player has previously been sent by a source, and the second being liveness, where every player eventually delivers every message sent by a correct source. Both these are very rudimentary. The second metric the paper observes is player behavior, and there are two kinds of player behavior the paper observes, one being rational and the other being trembling hand. So what is consensus? In committee-based blockchains, for each height, a committee is selected and is in charge of agreeing on which block to append next. In particular, at each height, the protocol used by the corresponding committee must implement the consensus. We say that a protocol is a consensus algorithm in presence of rational players if the following three properties hold: termination, agreement, and validity. Now let's take a look at the paper to see what these three terms really mean. So yeah, here we go. We say that a protocol is a consensus algorithm if the three following properties hold. One being termination. Every rational player decides on a value. So every rational player must decide that this is the block they want to publish and they have to choose a block. Second, agreement. If two rational players decide respectively on values b and b dash, then b is equal to b dash. That means that not only does a player need to choose a block, that it's that all players who choose a block have to choose the same block. Validity. A decided value by any rational player is valid. It's that every block that is chosen is having a valid properties. So the goal is to know whether consensus is guaranteed in committee-based blockchains in presence of rational papers. For this study, we use the notion of Nash equilibrium, which is intuitively a stable situation where no player has an incentive to unilaterally deviate, which essentially means that once the player knows what other players are doing, he cannot make a decision that will cause only him to profit and the others to lose out. Now let's talk about the protocol, the ideal protocol, which is the protocol for honest players, who are players that will stick by the protocol for sure. So a proposer is selected for the current round. A proposer is selected every round by the committee, and a proposer is only one person who proposes this is the block that we should publish, and he sends this block to the rest of the committee players. Once a player receives the proposal, he should check its validity and vote for the block only if it is valid. Otherwise, it should not vote if the proposal is invalid. At the end of the round, all committee members collect all the vote messages and count them. And since every vote is going to every member, they should all have the same number of votes with them. Let V be the number of votes required for a block to be considered produced or published, which is the decision of the consensus. If the proposal receives votes for at least V different committee members, then the block is considered as produced or published. Otherwise, the next round starts with a new proposer proposing a new block, and the procedure restarts until a decision is made. So, we are able to take such guaranteed assumptions because we are assuming that this protocol is for honest players. Let's take a look at the protocol in code. This is the prescribed protocol in code. As you can see, at initialization, the vote is nil, time is 0, and he's not decided anything. Round propose. In propose, we first check that if I is proposer. So, this is only to check whether he is a proposer, and he sends a proposal and he broadcasts it. Delivery phase here is just delivering the proposal to everyone, and the compute phase is everyone taking this proposal, checking whether it's valid, and then deciding a vote. Now, in round vote is where you send your vote across. In the send phase, if you are voting and your vote is not nil, you broadcast the vote. In delivery phase, you collect all the votes at the current height, and in compute phase, you sum up all the votes and decide whether the positive value is greater than a predefined value, which is defined for the success of a block. If it is greater, you have published your block. If it's not, your vote is reset to nil and you go to the next time frame. Now let's take a look at the protocol for rational players. And before taking a look at the protocol itself, let us look at the costs that rational players or any players part of this system incur. So there are 4 different costs, one being K, one being R, one being C check, one being C send, and these are really important. What is K? K is the cost incurred when an invalid block is produced. R is the reward when a valid block is produced. C check is the cost when you are validating a block, and C send is the cost when you are sending across your vote. Please keep in mind that C check is greater than C send, as this property will be used later. At each round T, when a player is receiving a proposal, he has 2 options for checking and sending, and since he is a rational player, he might or might not check, and that's why there's a false true option, and he might or might not vote, that's why there's a false true option for send as well. So let us look at the protocol for rational players as well. I'll only go through the differences. The difference is that in compute phase, he does not need to check whether the proposed block was valid or not, and he can still decide a vote. That's the main difference. So this compute phase is the only difference between the honest proposal and the rational proposal. So this is the main strategy for rational players. This is the decision tree that encompasses the main strategies. So first you receive a proposal from a proposer. You have 2 options here. You either check the validity of the block, or you do not need to check the validity of the block. If you check the validity of the block is either valid or invalid, and for each scenario you can either vote for it or not vote at all, or again block is not valid, you can vote or not vote. And if you don't have any validity information, you don't know what it is, it's a gamble, but you can still vote or not vote. And we have 2 reward systems in our blockchain system, which this paper examines, one being reward only sender system and one being reward all system. This is an extremely crucial part of the paper. So the main difference is that the reward only sender is a reward scheme where players who have only players who have voted will receive the reward, which is R. And so this is done to encourage players to vote. And the reward all scheme is that if any block is published, any valid block, the reward goes to all players regardless of whether or not they've voted. And you'll see there are reasons why we prefer reward all as well. And as you can see from the equations, the only difference is in the starting. where we have r into 1. This 1 is essentially a function checking true or false, so it returns a 1 or 0. So, r into sending your vote into block produced at t minus k into whether it's an invalid block. If it's not, you get a 0 here, otherwise you get a 1, minus the checking cost and sending cost. The difference is between here that we check whether a player has sent his vote or not, and here we don't need to check whether a player has sent his vote or not. So, before we finally head on to the main results of the paper, let's just formally define Nash equilibrium in this context. So, let sigma be a set of sigma 1 to sigma n, which is a strategy profile where sigma I is the strategy of a player and strategy is what we have discussed before in our decision tree. We write sigma naught of I to represent the strategy profile where the player I deviates and the others continue playing their strategy. So, only one player is deviating in a Nash equilibrium situation, and a strategy profile is in Nash equilibrium if no player can increase its gain by unilaterally deviating. Finding this equilibrium. So, this paper looks at 8 different scenarios actually. So, we first look at 4 different subtopics. First we look at reward only committee members, reward only the committee members that vote where the members are rational. Second being reward all committee members where members are rational. Third being reward only committee members where members may be trembling, and fourth is reward only committee members, reward all committee members where members may be trembling. We study the different equilibria with respect to the value V, which is the minimum number of votes required to publish a block. So, we consider 2 subcases here, when only one vote is needed to pass a block and when V votes are required to pass a block where V greater than 1. So, now let us look at the situation rewarding only committee members that vote under the rational subcase. So, let us look at when V is equal to 1, therefore, only one vote is required to pass a block. There is only one Nash equilibrium in this case. In that equilibrium, we find that all players have to vote for a proposed block. So, let us look at the proof. The gain of a player is R minus C send. And by the way, when we only have rational members in our committee and no trembling players, there is no need to check the validity of a block because a player cannot make a mistake essentially. So, there is no need to check the validity, and we assume that all the blocks proposed are valid. So, the gain of a player is R minus C send. So, reward minus the cost of sending, and we do not need to take in consideration the validation cost. So, now let us assume that a player deviates and does not vote, and if he does that, still n minus 1 players are voting, which is greater than 1 obviously, and the block is still produced. But since this is only reward only committee members that vote scheme, the deviating player receives a 0, which is a loss, and that is why he does not gain anything, and that is why we maintain Nash equilibrium. And this is the only solution for a Nash equilibrium in this schema, and we can now prove that. So, let us assume that there are 2 players and both of them send different values. So, let us assume player 1 sends false and player 2 sends true. In this case, the block is produced because there is one player that is saying true and V is 1, so the block is produced. So, this player will receive reward R minus C send and the other player will receive 0. Therefore, it is impossible, and if the player who didn't voted, he would gain at that. So, it is impossible to have any other situation of Nash equilibrium, and in this schema the consensus protocols are satisfied. Now, let us look at V greater than 1 situation. There are 2 Nash equilibria that can occur here, either all players vote or no players vote. In the first situation, when all players vote, again the gain is R minus C send, and similarly if one player deviates and does not vote, his gain goes to 0, and therefore there is Nash equilibrium there because he does not gain anything. In the second case, where no player votes, their gain is right now 0, but if one player decides to vote, he cannot actually publish the block because V is greater than 1, and that's where his gain goes to minus of C cent, which is lower than the gain at equilibrium, and that's why we're at Nash equilibrium. So let us now prove that there is no more equilibrium. To do this, let us define a set called X of cent, where this set consists of all the players that have decided to vote. Suppose this set has less than V minus 1 voters. Let's assume a player who wasn't voting, say I, decided to now vote, and let us assume that this causes a Nash equilibrium. Since X of cent is less than V minus 1, the player who has decided to vote, whose gain would have been 0, is now minus of C of cent because he has not actually swayed the vote, and that's why there cannot exist Nash equilibrium, because if he decides not to vote, the gain would be 0. And in the second case, where it's greater than V minus 1, assume by contradiction that there exists a Nash equilibrium such that player I does not vote, say false. The gain at the equilibrium is now 0. If instead he deviates and votes, his gain will now be R minus C cent, which is greater than 0, and therefore a player is gaining by unilaterally deviating, and therefore we are not at a Nash equilibrium. It's also important to note that in our first scheme here, in our second scheme where no player votes, we are not actually reaching any termination, whereas when all player votes, we are reaching a termination and our consensus. Now let's look at a reward all committee members scheme under the rational subsection with V equal to 1. So again, there exists only one Nash equilibrium, which is when exactly one player votes and others do nothing. This will be getting a little repetitive, so I will only talk about the novel parts. So here, let us assume a player with index 1 votes true, and right now his gain is R minus C cent. If he decides to deviate, his gain would go from R minus C cent to 0, and therefore he is not gaining anything. And if someone who is not voting decides to deviate, his gain would go from R, because he doesn't incur any sending cost, to R minus C cent, and that's why we are at a Nash equilibrium. Let us now prove that there exists no other equilibrium. So let us take it that two players vote, or two or more players, but let's take it as 2, I and J. Suppose both are voting, so both are receiving reward R minus C cent, but say player J decides not to vote, his gain would become R, which is greater than R minus C cent, and therefore this is not a Nash equilibrium. Now let's look at the case where V is greater than 1, where there are exactly two kinds of Nash equilibria, one being exactly V players vote and the second being no player votes. In the first case, we proved that where no player votes, this is a simple proof. So your gain at equilibrium would be 0 because no cost is incurred. But if one player decided to vote, his gain would become minus of C of cent, which is less than 0, and therefore we are at an equilibrium. In the second case where exactly V players vote, suppose you are part of the V players that has voted, your gain right now is R minus C cent. If you decide not to vote, your gain would become minus C of cent, because your gain would become 0, which is less than R minus C cent, and therefore in that case you are part of a Nash equilibrium. And if you are a player who is not part of the voting group, then your gain would have been R, but you decided to vote and your gain would become R minus C cent, which is less than R, and therefore we are again at a Nash equilibrium. And again, to prove that there is no more equilibrium, it's a very simple proof. We take two cases, one being where the number of players who have voted is from 1 to V, and the other being where the number of players is greater than V. We assume in one case that one player switches from true to false, and in the other from false to true, and you can clearly see that his gain is actually increasing when he does this switch, and therefore there exists no other Nash equilibrium. Now let us reach the second and probably the most important and novel part of this paper, which is examining these two reward schemes but under the trembling hand feature, which is where players can make unintended mistakes. Now let us look at V is equal to 1 case. There are two Nash equilibrium here. In the first one, under the condition that k is greater than or equal to r minus c send plus c check by p, and we will be looking at where this condition came from. It's that all players check the validity of the proposal and vote only if it's valid. And the second case where we attain Nash equilibrium is where all players vote for the proposal without checking the validity. So now let us look at the first case. So here we are taking p, which is a new parameter, to be the probability that a player has trembled or committed an error. So the expected gain at equilibrium is 1 minus p, where he hasn't committed an error, into r minus c send, which is the reward, minus c check, which is greater than 0. And suppose now one player deviates and does not vote or doesn't check, its gain at deviation is 0. If it deviates and votes without checking, its expected gain at deviation is r minus c send minus pk, and which is only lower when we equate it to the first equation we have, and that's where we get this condition that k greater than or equal to r minus c send plus c check by p, and that's why we reach Nash equilibrium at this condition. Now we look at our second case, where we look at all players who vote but without checking the validity. The gain at equilibrium of all of these players is r minus c send minus pk, where k is the cost incurred due to failure. Even if one player deviates, the block will be produced in any case, no matter its validity, because v is equal to 1. If any player deviates by checking the validity and voting, he is incurring an additional cost of minus c check, and because c check is greater than c send, which is a condition we talked about before, his gain will now be less. And if the player deviates and does not check the proposal's validity nor votes, his expected gain is minus pk, because he will not receive the reward and only incurs the cost of it being a failure, which is again lower than our initial gain, which is r minus c send minus pk. Now let us prove why there are no more equilibrium. I won't be getting too into detail of this because the proof is very similar to the previous proofs that we've already seen. So the main crux of the proof is looking at different subcases. So in the first subcase, we look at when no player votes, obviously no block is produced and the gain is 0. And then we look at two other subcases, one being whether a player who is voting doesn't decide to vote, and that doesn't really make a difference because v is only 1. And the second being a player who is checking validity and voting, and again this doesn't really make a difference because if all the players are voting in our Nash equilibrium, the block will pass anyways and he is just incurring an additional cost. Now let us look at reward only committee members that vote under the Trembling scheme, where v is greater than 1. Here we have 3 Nash equilibriums, one being no player votes nor checks, 2 being if v is less than n, all players vote for the proposal without checking the validity, and 3 being the same equation. There is an equilibrium when n minus v plus 1 players check the validity of the proposal and vote only if it's valid, and the v minus 1 remaining players only vote without checking the validity of the proposal. So now let's look at the proof of these. These are pretty interesting. So first we prove that when there are no votes, so the gain at equilibrium here is 0, and if one person decides to vote, the gain would become minus of c of send. So obviously this is a loss and therefore we're at Nash equilibrium. Now let's look at the case where all players vote without checking the proposal validity, and here the gain is r minus c send minus pk, and if someone checks, then again it's very similar to the previous case which I already explained, so I won't be getting into the detail, but you get the same conditioning, and that's why we're at Nash equilibrium. And now we look at the third case, which is when n minus v plus 1 players check the validity of the proposal and vote, and v minus 1 remaining players only vote without checking the validity. So we can first note that only valid blocks can be produced following this equilibrium, and invalid blocks do not have the necessary v votes. the expected gain of a player not supposed to check is 1 minus p into r minus c cent. If it deviates and does not vote, his gain at deviation is 0. And if it deviates by checking and voting, only if the proposal is valid, he incurs the additional cost of checking, which is greater than sending, and that's why it's a loss. Now, the expected gain of a player supposed to check is 1 minus p into r minus c send minus c check. If he deviates and does not vote, his gain at deviation is 0 under this scheme, and if he deviates by voting without checking, then he is risking the committee to publish a invalid block. So, your gain becomes r minus c send minus pk, which is lower than the gain at equilibrium under the same condition. And again, to prove that there are no more equilibriums, we look at two subcases where x is greater than or equal to 0 and where x is greater than 1, and we check the different cases of whether a player voting and not voting will cause a difference, and they do get gains, and that's why these are the only 3 Nash equilibriums. And now let's look at the final scheme of rewarding all committee members with trembling. At v equal to 1, there exists a Nash equilibrium, only one Nash equilibrium, which exactly one player checks the validity of the proposal and votes only if it is valid, while other players do nothing. So, here in the strategy profile, the gain of the player checking is 1 minus p into r minus c send minus c check, and the gain of the other player is r. Other players is r. So, if the player who is checking deviates, he is putting the entire committee at risk, and the gain would now be r minus c send minus pk, which is less than the previous gain at equilibrium if we have our condition again. And if our player deviates and does not vote and vote without checking, the block is never produced itself. So, his gain would now become 0, which is obviously lower than the initial gain, and that's why we are at equilibrium. And again, we have the same proof to prove that this is the only. So, let's take a look at our final case where we reward all committee members where trembling participants are active, in the case where v is greater than 1. So, there exists Nash equilibrium in two separate conditions, one where no player votes, and the second where one player checks the proposal validity and votes only if it is valid, and exactly v minus 1 other players vote without checking validity and the other players don't vote. And obviously, in the case where no player votes, you won't reach the terminal condition that a block is being published. So, let's look at that case first. The proof for it is the gain at the equilibrium of any player is 0. In case he decides to vote or check, he's only incurring costs without being able to actually change the outcome of whether the block is being published or not, since v is greater than 1, and that's why we are at Nash equilibrium essentially. Now, let's look at the second case, which is much more complex, but let's break it down into 3 parts. But first of all, it is quite clear to see here that only valid blocks can be published in this equilibrium, because there's one player who checks, who first validates and who checks and then votes, and v minus 1 players vote without checking and the other players don't vote. So, only the v minus 1 players can vote for an erroneous block, which obviously will not be published because we need v votes to get published. So, let's look at all the 3 kinds of different users. So, first let's look at the players that do not vote nor check validity, who have an expected gain of 1 minus p into r, where p is obviously the error of the publisher making a mistake. Let I be such a player. If I deviates and votes without checking, all proposal will be produced no matter the validity. So, the gain of the player at deviation is now r minus c send minus pk, where he is risking invalidity and therefore he is losing out. And the second is when he checks the validity, again he is incurring the costs of sending and checking, which is lower than what we have at equilibrium, and that's why these players don't need to do anything. Now, let's look at the case where the players who are not supposed to check but to vote, the gain at their equilibrium is 1 minus p into r minus c of send. Now let's say he does not vote, then no block will be produced, and therefore his gain at deviation is 0. If he deviates by checking and voting, only if the proposal is valid, he incurs an additional C check cost, and that's why this is lower, since C check is greater than C send. Finally, we can analyze the one player who's supposed to check. So assume that this player is 1. So at the equilibrium position, his gain is 1 minus p into r minus c send minus c check. If he deviates and does not vote, no block will be produced, so his gain would become 0, which is obviously lower than 1 minus p into r minus c send minus c check. But if he deviates by voting and not checking the proposal's validity, it goes to r minus c send minus pk, which is lower than the gain at equilibrium, where our condition of k greater than or equal to r minus c send plus c check by p comes back. And that's why all these strategy profiles are indeed a Nash equilibrium, because no player out of these three kinds of players can increase by deviating. Now let us prove that there is no more equilibrium at this setting. So if there are less than v players supposed to vote, no block is produced. So one such player can deviate and not vote, economizing its cost. If there are more than v players supposed to vote, one can deviate by not voting and economizing that cost. We can show that the others main equilibrium candidates are not equilibrium by, first way is by contradiction. Let I be a player supposed to vote. Its expected gain at equilibrium r minus c send minus pk, while if I deviates by checking the proposal validity and voting only if valid, only valid proposals will be produced. So its expected gain will be 1 minus p into r minus c send minus c checked, which is obviously greater than the pk cost which we are incurring, and that's why this profile is not an equilibrium. Assume that there exists an equilibrium where v players vote, counting also those supposed to vote after checking, and the others do not vote nor check. In the first case, we looked at where v players vote without checking. In this case, suppose that there are players that plan to vote, at least 2, I and j, check the validity of the proposal and vote only if it's valid. In this profile, only valid proposal will be produced. Its expected gain at equilibrium is 1 minus p into r minus c send minus c check. If instead I deviates and always votes without checking the validity, its expected gain is 1 minus p into r minus c send, because he doesn't incur the c check cost, but because other people are checking, it's always a valid block, which is better than the gain at equilibrium, and that's why this profile is also not an equilibrium. So now we've looked at all these cases, and let's just have a final look at them. So this is the summary of the equilibria with rational players. Under the Reward-all scheme, when v is equal to 1, you have one proposition where only one message is sent and you have consensus. And in reward only sender scheme, when v is equal to 1, all the players send a message, you reach a consensus, but this is very inefficient because you are actually sending so many unnecessary messages only for them to incur a reward. And in the second case, when v is greater than 1, no message is sent, obviously that doesn't create termination, so that's not useful. And when v messages are sent, we have a consensus. Here no message is sent, no termination, and all players send a message when reward is only to senders. This is again consensus, but again inefficient because every player is sending a message even when not required. This is our scheme's summary for trembling players. When v is 1, if one message sent is valid, you reach a consensus. And reward only senders, either n messages always send, validity is not guaranteed in this case, and n messages are sent only if valid, you reach a consensus here, but again you are sending so many unnecessary messages. When v is greater than 1, no message is sent, you reach a no termination clause, and when n minus v minus 1 message is always sent, you get valid blocks and a consensus. whereas in reward only senders, no message sent, the same thing, no termination. If v greater than n, message is always sent, validity is not guaranteed, and when n minus v minus 1, message is always sent, plus n minus v plus 1 is valid, then you reach a consensus, which is the one we just recently discussed. So the conclusion is that this paper shows novelty in analyzing the behavior of rational and trembling players in committee based blockchains, and it is found that in all the cases there are equilibriums to be found, and in all the cases there are equilibriums which can lead to a consensus. But their final thoughts are that maybe we should be looking more at the reward all scheme on other than the reward only sender scheme, because as you can see, the reward only sender scheme is quite inefficient because it takes a lot of messages and therefore will actually delay the network and cause the blockchain to be even slower, which it's already a problem that blockchain is slower. So their consensus is that we should explore the reward all scheme more in the place of other kinds of players, because there is not much inefficiency. And yeah, this is our presentation of this paper. Hope you guys enjoyed it. Thank you.